Hello and welcome to the first video lesson for Geology 1050, Earth Through Time. This course is a 3 credit hour lecture course comprised down to just under 5 weeks. Therefore, this course will move quickly and cover what is normally discussed over the course of 15 weeks. My name is Thomas Gaetano, recent graduate of ETSU with a Master of Science degree in the Geosciences. I have experience teaching that ranges from state park environmental science programs to formal classroom education at the primary and collegiate levels. Teaching online has unique challenges, so please feel free to reach out via email if you have any questions or concerns. My contact information is available on the course syllabus. To access the materials for this course, go to the Geology 1050 D2L page and under Contents, select the syllabus, textbook, or lecture video modules. You can download or view at will. Lecture videos will be required content for the class as well as quizzes that will test your understanding and applications of the lesson material. Keep in mind that both the lecture and the lab sections will each have their own set of videos and assessments. This course will also host live Zoom meetings that are intended to function as an opportunity to promote collaboration and teamwork and have broader discussions about the lesson material in a discussion format. During this time, you can ask questions about the lecture videos, quiz questions, lab section, or the textbook itself. Geoscience, to me, is challenging not just because it has a whole vocabulary of technical terms, but also because it operates on systems of reasoning that may come naturally to those who excel at puzzles or riddles. The fundamentals of scientific processes in geology and paleontology will be covered in the first lessons of this course, before shifting to general biology and ecology and ending in comparative anatomy of skeletons and the history of life as told by the fossil record itself. In other words, we must understand the foundations of how historical geology operates before you can understand and accept the resulting knowledge about Earth life in the distant past and how it has changed through time. For this reason, I encourage you to follow along in the textbook from lesson to lesson, since this course will be structured around the book. Don't worry so much about the geoscience technical vocabulary for now. That's what I'll be attempting to translate in these videos and during the live meetings. In the past, the course grade is based on large exams worth 100 points each. In this online platform, I instead am breaking the points down across smaller quizzes that can be taken immediately following the videos. My intention is to assess your persistent engagement in the lessons, understanding of the main ideas, and applications that result in our understanding of the distant past, rather than long-term retention of the factual knowledge that's presented in the course. The way I see it, you can either come away from this course with the entire sum of knowledge regarding the history of life on the planet, or with an understanding of the methods used to pursue the understanding. Then you will have the tools needed to see through paleontology mistakes that are reported in the news, in documentaries, or even portrayed in Hollywood movies. Holy cow, that movie was still awesome though. I will try to follow the schedule as much as possible, but keep in mind that it is subject to change. And the syllabus details student and technical resource information. Please consult this information. Okay, now with all that said, what exactly is this first lesson about? Well, it really is about understanding the difference between historical geology and physical geology. And the difference is time. Physical geology is the study of the Earth and what changes it as we observe in the present, whereas historical geology takes our understanding of how the natural Earth-forming mechanisms operate and uses it to investigate how the Earth used to be before humans were around. The scientific method is tricky to apply to historical geology because it deals with the distant past, but it is possible if we use multiple science disciplines. Therefore, historical geology can be divided into the immensity of geologic time, plate tectonics, and biology. Historical geology research tells us that at different times throughout Earth history, the planet would be unrecognizable in its climate, geography, and the plants and animals on land and sea. This gives paleontologists the ability to imagine ways in which the Earth could be different in the future. Historical geology researchers can speculate on future changes because we have learned a lot about how the planet responded to changes in the past. To succeed, historical geologists must see the results of the change in the past, then uses the natural and physical processes of Earth in the modern day to investigate the causes of the change in the past. I like to think of it as reverse engineering the ancient past. This can be used for a variety of humanitarian causes, like predicting the behavior of hazardous geological events like volcanoes or earthquakes, or in the quest for new energy resources. Regardless of the intent, you can count on some combination of biology, physics, chemistry, and more. And for this reason, historical geology can be a challenging, integrative science to learn. However, it is not impossible to learn, so let's discuss the scientific method and how it is used in historical geology. The core of the scientific method is intended to provide a template to investigate natural processes behind objective observations and objective data. Objective meaning that it is consistently observed from person to person and not specific to an individual's perspective, which would be subjective. Using the scientific method, one can make an observation about the natural world and with an acknowledgement of ignorance form a question. I wonder why that is the way it is. Then you study it, figure out how to measure or quantify what you observed. Based on what things are correlated with what, you make a hypothesis that explains it. Finally, and most importantly, the hypothesis must be tested and tested and tested and tested and tested. If the hypothesis is true, then it should lead to predictable outcomes in future tests. If a hypothesis is true, then the resulting knowledge is very likely to be correct, and scientists will refer to it as a theory only after it holds up to repeated testing. Now, the textbook describes an example of the scientific process in a geological context, but to be honest, in this class, we haven't learned enough about the background geology and vocabulary enough to make it feasible to discuss in this video. So I will leave that as a potential discussion topic during a live meeting, or to be dealt with in more detail in future lessons. For now, let's come back to the three themes of this class: deep time, plate tectonics, and biology. If we watched a landscape, say a mountain with rivers and streams coming down from it, for just one day, we wouldn't really see much change. But if we took a picture every day for 1,000,000 years, you would see the mountains being carved up by the river and the valleys being built up by what came off of the mountain. So how do we have objective evidence for the absolute age of rocks? Well, it is in the radioactive nature of certain atoms and the stuff that these atoms are made of. In fact, some atoms are constructed in a way that isn't very stable. This atom would be in the parent stage. Now, to become stable, atoms eject smaller than atom particles from their center at consistent rates over long periods of time. The result is a transformation into a new, more stable atom called a daughter atom. This means that a rock with unstable parent atoms have a built-in clock. And by measuring the amount of rock that has transformed into the stable daughter, plus the knowledge of the rate of this transformation for this specific parent-daughter relationship, then we can calculate the absolute age of the rock sample. This method is appropriately named absolute dating. And other ways of dating include relative comparisons of rock layers that are either older than or younger than. The relative dating method is still used to date fossils and rocks. And the reality is that both are needed in order to accurately interpret the rocks and fossils in terms of Earth history. And the details and methods of dating the age and fossils and rocks is the subject of your first lab assignment. Tectonics is the next theme of this class, because over the last half a century or so, we've found that a lot of Earth is the way that it is because of plate tectonics. Now, tectonics can be understood if we zoom out and study the breaking patterns of rocks across the entire surface of the planet. If we zoom out enough, we find that the layer of earth beneath our feet is broken into several pieces called plates. And the edge of each plate is either colliding, sliding past, or moving away from other plates that share plate boundaries. And the impact of plate tectonics on the history of life on Earth is the topic of Lab 2. Finally, the last theme is biology and the evolution of life. Now, the book makes it very clear that evolution is the way living systems move through time. I found this to be a nice correction to other definitions that may lead one to think that evolution is the way individual plants and animals change through time. The mechanism of change that acts on living systems is natural selection. Now again, the details of how the mechanism functions will be covered in Labs 3 and 4. But let me just summarize by saying that the primary goal for any living thing is to survive to adulthood and then pass down the traits that help that animal survive long enough to reproduce. If the environment is one way, then a set of traits, or adaptations, helps animals achieve the primary goal. But when the environment changes, then those traits prevent the animals from achieving the primary goal. Then, new traits from different animals with unique adaptations begin to achieve the primary goal at a greater success rate than the animals that came before. The result is the slow change of animal morphology by the movement of these traits, adaptations, and most importantly, the genetic material at the foundations through generations of animals, or just think of it as that material moving through time itself. This is why animals look very different at different stages of Earth history. Now, this lesson is meant to be introductory, so we will come back to each of these themes in future lessons. It is essentially a summary of the first chapter, so consult the text and feel free to ask me questions through email as you are working on your first assessment for this video. I will never put time limits on your assessments other than the weekly deadlines, so if you get stuck on a question, you can email me or bring it up during a live class meeting, and I'll be happy to work with you. The next lesson will be a review of the history of research from the about 18th century through to the modern age. And the last lesson for week 1 is a more in-depth look at how we date the age of Earth. Remember to keep checking your lab section's D2L page because you also have 2 lab assignments for the first week in that lab section as well. Thank you again for listening.